All right, so let's go over problem of the day 19. This was one of our conjugate addition reactions. Hey, you guys? It's hard to hear. So with this reaction, we've got a conjugated diene. So we've got alternating double, single, double bonds. These have unique reactivities. So let's do the first one. Does it matter which alkene I use for the nucleophilic attack? No, because they're symmetric, right? Both are equally likely, so I'll just pick one. This alkene can attack, kick off the bromine. Now the question becomes, where will our carbocation be? I'm going to draw it. Oops, just 1 second. Will our carbocation be at this location in green or this location in blue? Blue, right? Why will it be on that blue carbon or the carbon indicated by the blue arrow? Oh, it's more substituted, but there's something else that dominates. Resonance, right? So if we look at this, we're going to install the proton on this upper carbon. We'll get a carbocation here, and this results in a resonance stabilized carbocation. Oops. So we can delocalize this carbon, or this positive charge to this carbon. So make sure you're comfortable with resonance from first term. Now we've got bromine floating around, or bromide I should say, and the bromide can attack either carbocation. So I'll show it this way. Do we have to worry about stereoisomers here? What do you guys think? Yes, so that bromine can attack either the top lobe of that carbocation p orbital or the bottom lobe. So I'll just draw one of them. I'll write Br plus En for enantiomer. And then with the bottom one, this bromine can attack this carbocation, and again it can attack from the top or the bottom. Let me finish drawing in these hydrogens. And we'll end up with a mixture of isomers for this one as well. All right, now the question I didn't ask, but I could have. Which one is our 1,2 addition product? The top one? Why is that? Yeah, exactly. When we're looking for our 1,2 addition product, we want to compare where that bromine is to where the hydrogen is that was added in. In this case, they're added to adjacent carbons. So this will be our 1,2 addition product. What about the bottom one? Is it a 1,2, 1,3, or 1,4?
1,4.
1,4. So in this case, we want to count. So we go 1, 2, 3, 3, 4, and this will be our 1,4 addition product. All right, when we think about our kinetic product, will that be our 1,2 addition or our 1,4 addition? 1,2. 1,2 is always going to be our kinetic product, so I'll just write in kinetic. And which one will be our thermodynamic product? 1,4. It's not always 1,4. We saw an example yesterday where our kinetic product was also our thermodynamic product. What's the main defining feature when looking for a thermodynamic product? Yeah, the substitution of the alkene. So if we look at the bottom one, we've got a tetrasubstituted alkene. The top one, we have a trisubstituted alkene. So, so this will be our thermodynamic product. Does that make sense? Always double check your alkenes. Don't just assume that 1,4 will be your thermodynamic product. A lot of organic chemistry students make that mistake.
What's the reason why we consider it as a thermal one?
Because the alkene in that bottom one is tetrasubstituted. The alkene in the 1,2 addition product is only trisubstituted. It only has 3 substituents coming off of the alkene.
Okay.
You want to form your most substituted alkene when you form your thermodynamic product. All right, let's do the next one. Again, this is symmetric, so we can have either alkene attack. We always want to form our resonance stabilized product. So in this case, our carbocation will be on that more substituted carbon. and we can have this delocalize. And we get these two resonance structures. Now when we have bromine around, this bromine can attack either one of these carbocation centers. And so I'll do the top one first, and then the bottom one underneath. When we do this, we again have to worry about stereoisomers with the top one, right? And is this going to be our kinetic product or our thermodynamic product? Kinetic. Again, this is 1,2 addition. We installed the bromine right next to where we installed the hydrogen. So this will be our kinetic product. And then if we look at our product for this one, we've installed a bromine over here. And is this our thermodynamic product?
Yes.
Yeah, because we are forming a tetrasubstituted alkene. So in this case, our kinetic and thermodynamic product are different. All right, hypothetical situation. What if I want to get this top product, not that bottom one? Sorry, that's hard to see. There we go. Cold, right? If we ran it really warm, we would exclusively get that bottom one, or at least get it in a majority. If we want to isolate our kinetic product, oftentimes we have to run these reactions really cold. So if you were in a lab, a common technique that's used is you will actually get dry ice and acetone, the same acetone we use to clean our IR, and you make an acetone dry ice bath that goes down to negative 76 degrees Celsius. It is very cold, and it will prevent the thermodynamic product from forming in these cases. So if you ever go on and work in a chemistry lab, it's pretty common to see acetone boxes in the room so you can set up those reactions.
You just reminded me, there was in the news, I think it was like last year, a lady, she was young, she just finished school, and she worked at somewhere, and she locked herself into a cold room. Do you know anything about that?
I don't, yeah.
It was something to do with kind of like it was science. I wasn't good at reading that, but
Yeah, I'd have to look it up. There's been a few major lab accidents in the past few years.
she froze and she couldn't get out.
Yeah, it's always a good idea if you have a walk-in fridge to have an emergency I need out button. Yeah. All right, so let's continue on to the next portion of chapter 17, which covers the Diels Alder reaction. The Diels Alder reaction is one of my favorite reactions. And we saw an intro to it yesterday when we were covering pericyclic reactions. And we said in a Diels Alder reaction, you have this diene. And we have different nomenclature for dienes, right? We referred to them as S-cis or S-trans. What is this one going to be? Is it going to be S-cis or S-trans? S-cis. S-cis, because if we look at the single bond, the substituents coming off of the single bond are on the same side, so they are cis to one another. And so we're dealing with an S-cis diene. So diene just means we've got two alkenes. The other component that we have in the Diels Alder reaction is our dienophile. And I'll just put an X substituent coming off of there. And we'll label this as our dienophile. And during the Diels Alder reaction, one hint I find really helpful is draw a dashed line to indicate where these will connect. You'll always connect the termini of your diene to the two carbons on your dienophile, specifically the two alkene carbons. The first step is we'll take this pi bond from our dienophile, and it will form a new sigma bond where that dashed red line is. Then what's the next step?
The double bond on the diene will go to the sigma bond to create the pi bond.
Yeah, exactly. We'll have this cyclic flow of electrons, and then last step? Yeah, we'll take this pi bond and form a new sigma bond. So if we are keeping track, we can say we broke 3 pi bonds in this reaction. And then let's draw our product for this reaction. Do we have any pi bonds that form?
Yes.
Yeah, if we look over to the left, we formed a new pi bond, so we need to show that. So we make one pi bond. And then we also make 2 sigma bonds. So if we look at our new sigma bonds are right here. Whoops, sorry. Yeah, right there and right there. And our new pi bond that we formed is right there. So we've broken 3 pi bonds, but we've made 2 sigma bonds. What's stronger, a sigma bond or a pi bond? Pi bond. Yep.
With the X coming off of the...
Yeah, I need to add that in. So we could have this X coming out right there. And so with the Diels Alder reaction, oftentimes we have a substituent coming off. And this X substituent is typically an electron withdrawing group. And so that's called a normal demand Diels Alder reaction. So I'll make a little note here that X equals an electron withdrawing group.
Will we have an enantiomer for that? Or maybe a dash or wedge?
Yes, you could end up with an enantiomer for this, so we'll write plus En as well. So I'll give you guys a couple of warm-up problems, and I want you guys to help me predict the products for these Diels Alder reactions. The first warm-up I've got utilizes the same reactant that we had in our problem of the day. And I'm going to have Cn and Cn. So nitriles, those carbon-nitrogen triple bonds, are quite electron withdrawing. So what will the product be for this reaction? Raise your hand if you think you've got the product already. All right, so it looks like most of you have got it. Like we did up here, I'll draw in our dash to show where we're making our new sigma bonds. Again, we'll take the pi bond from our dienophile, form a new sigma bond, wrap this around, and wrap this one around. So our new product actually has 2 different rings in it. And we've got our nitriles coming off of the ring to the far right. So you can see the red dash lines that we formed. We've got right here and right here. So we've created those 2 new sigma bonds, and we've created a pi bond on the left. Yep.
Can we put that pi bond on the first one, on the first ring?
On the first ring, well, if you look at it, right, this whole ring is still hanging out off of the left, and we've formed the pi bond on that rightmost green portion, so we don't want it to go all the way over to the left side of the ring. So keep track of which carbon-carbon bond you're forming your pi bonds between. Yep.
Do the CNs have to be dashed to be wedge?
In this case, you could have dashes or wedges, but in this case, let's think about this. Does this have stereochemistry?
No.
What's going on here? Plane of symmetry. What do we call molecules that have stereocenters but a plane of symmetry in them? Meso compounds. So you could draw it as both dashes or both wedges, but you're actually drawing the same thing. Yeah. All right, let's do another one.
You have a question?
Oh, sorry.
It's always going to be cis and never trans?
For the nitriles, we'll actually get into that, but one thing, I'll give you kind of a preview. If you look at the nitriles here, you see how they're cis to one another coming off of the alkene? That means that your Diels Alder product will have them cis off of your cycloalkane, right? So in this case, they're going to be on the same side of that alkane that you form. All right, I've got another one for you guys. This is one I used to always put on my exams, and students would get angry at me. Well, What will the product be for this reaction? Before you guys overanalyze this, let's analyze our diene and our dienophile. Which one's our diene? It's the left one, right? So we'll label this as our diene. This is our dienophile. Our diene, is it S-cis or S-trans? Trans. Do you think an S-trans configuration will work well for Diels Alder reaction? Not really. You could try to draw a product for this, but everything's going to get way too strained. So if we look at this, this is S-trans, which means that you will have no reaction. So make sure anytime you do a Diels Alder reaction, you double check to make sure that your diene is S-cis and not S-trans. In this case, it's S-trans because these are going in opposite directions off of that sigma bond in between them. All right, I've got another one. Whoop. In this next one, I've also got a diene. And I'm going to use a pi bond, or an alkyne with 2 pi bonds. Will it work?
No.
Well, let's take a look at the top one. If we look at the top one, is there any chance of having that rotate into an S-cis conformation? No, because we've got it kind of tethered up into a ring, right? What about this bottom one? Yeah, definitely. So, the other day I talked to you guys a little bit about, let me erase this. The energetic barrier to go from S-cis to S-trans. Does anybody remember the temperature? 15 kcals per mole. So 15 kcals per mole. And if we do this, we can go from S-trans to S-cis, assuming it's not locked into a rigid conformation. Now that we've got this S-cis conformation, we can have it react with our alkyne. So the question is, what will our new product look like?
Why we use kcal per mole instead of joules?
Because chemists and physicists never agree on anything.
Great.
No, some chemists will use kilojoules per mole, but a lot of American chemists have continued to use kcals per mole.
But that's not yes a unit.
It's not, but it's the same thing as why do a lot of engineers measure things in inches? It's just been tradition. We should all use kilojoules per mole, but you see it quite often in textbooks as kcals per mole. Did you guys hear about the Mars lander? I think it was in the early 2000s. So the engineers were using imperial units, the physicists were using SI units, and they plowed it into the surface of Mars going over 200 miles an hour because of their math mistakes. So always double check units. All right, so let's do our Diels Alder reaction. I'm going to connect these with our dashed line just like we saw before. We'll take one of these pi bonds. We'll have it hop down. Another pi bond will hop over here. Another pi bond will hop over here. So we are going to form a new ring. We've got this pi bond. Is that the only pi bond we have now? No, we have a second pi bond from our dienophile, right? That alkyne has 2 pi bonds, so we have one of those remaining. And then these 2 R groups are still coming off.
Are they dashes or wedges, or are they not because they weren't?
That's a good question. Do you think there'll be dashes or wedges?
No.
No, because if we look at these,
Planar.
right, these are sp2 carbons. They're planar. We don't show planar carbons or planar substituents with dashes or wedges. They're not going in or out of the page.
Okay, so what reactors will we
Yeah, when we start doing synthesis activities, you'll be able to use Diels Alder reactions. When we talked earlier, I think it was in chapter 10, I said that the Grignard reaction was one of the first reactions that was used to make new carbon-carbon bonds. This was a game changer because this was really easy to make carbon-carbon bonds, and it works on a whole variety of different systems, and it's very stereoselective. So we'll talk about that a lot more. But this is a much more elegant reaction than throwing a Grignard at something. All right, let's do a little bit of an investigation with what's occurring at the molecular orbital level. Yeah. So yesterday we talked about the molecular orbitals for conjugated systems, and I made some models for both our diene and our dienophile, so we can see this three-dimensionally too. So if we look at this, this is our diene, right? Is this S-cis or S-trans? Cis, right? So if you look at this, this would be like our diene right here. I've got the p orbitals lined up in the front and back, and then this pi bond is aligned right here and here. When you do the Diels Alder reaction, essentially what you're doing is a docking mechanism, right? So your diene is going to dock onto your dienophile, and in order for this to occur, you have to have the correct phases for your p orbitals. So if you look at your diene, one of them has a blue lobe sticking down, the one in the front, and the one in the back has a red lobe sticking down. That means in order for this docking to occur in phase, you're actually reacting with the lowest unoccupied molecular orbital of ethylene. So it does require a significant amount of energy in order to excite ethylene all the way up to the LUMO level so that it can dock correctly. But we're going to study this mechanism in a lot more detail, but I just wanted you guys to have an idea that it doesn't go together like this. It's not a head-on collision. It's more of a docking mechanism between the two reagents in the Diels Alder reaction. All right, so let's continue on, and we're going to talk about the reaction stereochemistry.
That's not a pretty stable formation, isn't it? It's like both.
Yeah, but boths can be stable. They're relatively stable, right? Everything's relative. So I've got a little video, too, that does a better job of showing this reaction. I may have to open my other one up. All right, so you can see the diene on the right. The dienophile is on the left. And we're going to see how it docks. So you've got your diene, it will hover over your dienophile. And then you form kind of this three-dimensional structure of your new Diels Alder product, where you've got your double bond on the right and your adducts coming off of the left-hand side. So we're going to look at this in more detail, but if you want, I've got the video posted in the notebook, so you guys can watch it a few times if you just need to see it three-dimensionally. And I'll try my best to represent this two-dimensionally. So let's take a look at one situation. This is our cis dienophile. All right, so we've got our diene, and I'm going to choose a similar dienophile to what we had before.
In this lesson, we're going to take a closer look at how frontier molecular orbital theory can help us explain.
Playing YouTube in the background. There we go. Sorry. Here's our cis dienophile, right? So we've got substituents coming off cis to one another. We've got our diene on the left, and we said when we react these together, you'll have a docking mechanism where your diene will hover over that dienophile. This pi bond will hop over, this pi bond will hop over, and this pi bond will hop over. And these two nitriles are going to be cis to one another coming off of the ring. So cis, and then these will be cis as well. So if you start out with a cis alkene, you're going to get a cis product. So both of those nitriles will be facing the same direction. You're not going to have one sticking one direction, so pointing towards you, and one going away from you. They'll either both be dashes or both be wedges. Is this something where we have to be worried about stereoisomers? No, this again is going to be a meso compound, so we don't have to worry about it too much. Let's take a look at this using a few different drawing techniques. So what I'm going to do is I'm going to show you guys the top-down view. All right, and with the top-down view, I'm going to show the dyene kind of in front. So if you guys look at my molecular model kit, this is our dyene, right? So we've got our double bonds essentially here and here. And then underneath it is going to be our dienophile. So we're going to do the docking. And I'm going to show it using my best artistic abilities. Let me erase these double bonds. And during the transition state, we're breaking these pi bonds, so I'll show them as a dash. We're making this pi bond, so I'll show it as a dash. We're making this sigma bond, so I'll show it as a dash. We're making this sigma bond, and I'm showing it as a dash. And we're breaking this pi bond. So this is our top-down transition state. And then our final product, if we look at it, we'll still have this kind of boat-like conformation. Whoop, let me clean this up. Where this portion of our boat is coming towards us. We formed a new pi bond right there. And then going back, whoops, we've got these hydrogens sticking up and these nitriles sticking down. Sorry, I know this is not my most elegant artwork. Let me try to extend this a little bit. So can you guys see that kind of boat conformation where both nitriles are sticking in the same direction?
Yes.
Okay. This is one of those things where sometimes building the model will help you see it three-dimensionally. The other way that I really like to imagine this is the side-on view. So let's draw our transition state for our side-on view. So this is our dyene. So instead of viewing it like this, where we're doing a head-on view, we're looking at it from a side view. So I'm trying to draw it with a little bit of perspective. And then underneath it, we'll have it docking with this nitrile. Whoops. Where we've got CN here, CN here, got hydrogens, and we're forming a new sigma bond as these are docking down, breaking this pi bond, breaking this pi bond, breaking this pi bond, and making that pi bond. So this is similar to that docking mechanism you saw in the video. So we're docking them side-on view like this. And that will help explain a lot of the stereochemistry for this reaction. And if we were to draw our final product this way, it would look like this, and we'd have our hydrogen sticking out here and our nitriles sticking out right there. Quite often students will ask me, what way is most appropriate to draw it? Can I draw the product using our 2D bond line structure, so the one I have in the top?
Yes.
Can I draw it in the boat structure?
Yes.
Can I draw it in this structure? And the answer is yes, right? You can draw it any way you want, as long as I can clearly see stereochemistry. So pick one that works really well for your method of learning and try to stick with that, but be able to interpret all of these different views. They're just looking at it from different perspectives. All right, let's do a different one. This one's going to be our trans dienophile. So again, we're going to start out with our diene, and I'm going to make it simple, so we'll stick with nitriles here. And we should try to be able to predict our Diels Alder product in this case, including its stereochemistry. So we'll put our dashes in. We'll take this pi bond, swing it over. Take this pi bond, swing it over. This pi bond. So we've got our pericyclic reaction. We'll do our 2D structure. So one of these will be on the opposite side of the ring of the other. So if we look at this alkene, they're trans, right? They're facing opposite directions of the alkene, which means that our substituents, one of them will be facing back into the board and one will be coming out of the board. So again, we have to match cis and cis and trans and trans. Do we have to worry about stereoisomers? Yeah, because no longer are we looking at a meso compound. This doesn't have an internal plane of symmetry. So what I'll do is just write plus En. Do you guys want to see the boat view and side-on view? No? Fair enough. All right, let's look at our tetrasubstituted dienophile. I'm not going to lie, when I learned this, I was like, what is this guy drawing on the board? It's really tricky because of the three-dimensional structure, especially when we get into more complex systems. But let's take a look at the tetrasubstituted one first. So I'll do a nitrile here, and then I'll put different nitriles on the other side in different colors. And let's try to predict what our product would look like. Do we have to worry about cis or trans?
Yeah.
Well, in terms of colors, yeah, but we've got 4 identical substituents coming off. So let's look at our product. We could have both of these cyano groups that are drawn in black coming off the same side. And our other cyano groups would also share the same side. But in this case, it doesn't really matter for a tetrasubstituted dienophile, right? Because this is an achiral molecule. I just wanted to show that we're not doing anything tricky here. Yep.
But, I mean, you could have some of those tetrasubstituted where the substituents weren't all the same, right?
Yes, exactly. And that's when you do need to make sure that they're on their correct respective sides.
Could you have, I don't know if tetrasubstitute is the right word, but could you have a more substituted diene?
Yes.
And have it still work?
Oh man, you're stealing my next problem. Let's do a challenge one. So the question is, what would happen if we changed our diene to something that's not a simple diene? What if we've got substituents coming off of it? So for this one, I've got this diene. Oh, that's a long bond. And we're going to react it with our tetrasubstituted dienophile. What will our product look like? I'm going to draw the dreaded boat conformation. All right, so this is our diene.
Wait, what is your fancy?
What's that?
What is
No, I'm just going to get started drawing this. I'm not going to show you the answer, but I wanted to help you guys get started with the boat one. Right, so if we think about this diene, we've got one methyl group kind of pointed in, the other one's kind of sticking out. And then I'll draw our dienophile back here. So CN, 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 CN. So we're doing this top-down view, right? Raise your hand if you think you've got this. All right, looks like a good portion of the class has. So let's use our top-down docking mechanism. So we've got our diene drawn with the methyls coming off in the correct positions. And I'm going to erase these pi bonds so that we can draw our transition state. Just like we saw before, we're going to break this pi bond. We're going to break this pi bond, and we're going to break that pi bond. So I'll draw those as dashes. We're going to make a new sigma bond here and here, and we're going to make a new pi bond right here. So this would be our transition state for our top-down view. And if we go to our product, I'll try to do perspective here. We've got one methyl group sticking up here, the other methyl group's still in that same position, and the hydrogen's here, hydrogen's here. Oops, let me slide this over. And then underneath, we've got this nitrile, 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 nitrile. We formed a new sigma bond. We formed a new sigma bond. Whoops. And then we've also formed a new pi bond down here. Right? Does that make sense? So the question is, how can we draw this in a more elegant form than the crazy boat structure? It has its charm. I think the easiest way to do this is to imagine looking straight up and down onto this boat. So imagine your eyeball looking directly vertically down.
Is it a double bond on the bottom?
Yes, double bond on the bottom. Let me try to emphasize that more. Right? So let's imagine we're looking straight up and down, and I'll call this the top view. So let me actually draw my little person here. It's our Cyclops looking down. So this is going to be the top side. This is going to be our bottom side. If we think about this, that means that our double bond's going to be to our left, right? So if we're looking straight down on top of it, the double bond will be to our left. What about up here? Will the methyl group be a dash or a wedge? A wedge, right? Oops. Because it's coming closer to our eye than that hydrogen, this methyl group will be shown as a wedge. What about the one on the bottom? A dash, right? Let me erase my little person here. I think I proved the point. There we go. And then what about the nitriles? They'll be coming off the right, but does it matter if we draw them as dashes or wedges? No. So we could have CN, 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 or CN. Do we have to worry about enantiomers? Yes. Yeah, because this is not a meso compound anymore, so we may end up with a mixture of enantiomers out of this. So if you think about your diene can attack either from the top face or the bottom face, so you'll oftentimes observe a mixture of stereoisomers out of this. Do you have a question, Sam?
Yeah, so if you put the top as a dash and the bottom as a wedge, would that be wrong?
No, that would be one of the possible stereoisomers. Yeah. Yep.
Does the CNs have dashes or wedges?
In this case, you could draw them as dashes and wedges, but oftentimes, like with the tert-butyl group, if there's no stereochemistry, it doesn't really matter. So you don't have to. Yep.
Is the why didn't we have the double bonds drawn? Is it just assumed with the dashed lines? Are we just showing the
So,
moving?
are you saying right here, why am I drawing these as dash lines?
No, why didn't we draw the double bonds? Is this the movement right now?
Yeah, what I'm drawing in that top-down view is the transition state view. So it's in between bonds being made and broken. All right. You guys ready for another challenge?
Yes.
Daniel looks like he's ready for it. All right, so we've got this as our dyne. Whoops, let me clean this up a little bit. This is called cyclopentadiene. It's the same reagent I gave you on the problem of the day. And we're going to react it with something a little bit fancier than what we've seen. This is going to be our dienophile.
What is Exo?
We're going to talk about that.
Okay.
So the question is, what happens when we combine these two reagents? So I'll let you guys try to do the arrow pushing and come up with some predictions. I told you guys, three-dimensionally, this is not easy stuff.
You're not going to mark this down for not being good artists, right?
I need to be able to at least decipher your stereochemistry, but it doesn't have to be pretty. You guys can tell my drawings aren't always the prettiest. So this pi bond we know will hop over, this one will hop over, and this one will hop over, right? Just like our normal Diels Alder reaction. So let's draw in our potential products. Oops. So I'm going to draw it kind of as a roof. So can you guys see how these carbons shown in blue are now going to become our roof carbons? So they're kind of sticking up and out, which means that over here we've got bonds going to this guy, right?
Is that a dash?
Yeah. So these are still sigma bonds in between here. So that guy.
Are you using double bonds in your leftmost ring?
Oh, yes. Thank you. And then we've got this double bond here. But then there's even more stereochemistry, right? So we just looked at this stereocenter, and we said that that blue portion of the dyene, that house or the roof, kind of sticks up, and the dienophile will be underneath, so we're doing that docking mechanism. But we've got some more stereocenters in there. We've got this stereocenter, and we've got this stereocenter. So it gets tricky. Let's do a couple drawings, and again, I'm going to resort to drawing it in the side view. And we've got two possible pathways. The first one is called Exo Addition. The other one is called Endo Addition. All right, so let's imagine we've got our cyclopentadiene right here. And we've got our dienophile that's kind of docking underneath it. Right? I'm going to slide this up so everyone can see. So we had our double bonds here, here, and here, and we're docking, kind of like an alien spacecraft. And we're going to form our new sigma bonds between these carbons, right? And we're forming a new pi bond right here, but we're breaking this pi bond, and this pi bond. So this is our transition state. So let's take a look at our final product for this one. This is challenging your artistic abilities. And we've got this right here. So can you guys kind of see that? We're docking it, and the new 5-membered ring's kind of sticking out and away. This is called Exo Addition, primarily because that ring is not underneath. So it's not like an alien docking right above you, it's more offset. And then the endo mechanism is similar but reversed. So we still have this dyene, but this time we have our dienophile facing inward. So let's take a look at this side-on view transition state. So just like before, we're going to form a new pi bond right here and here. We're going to break this pi bond, break this pi bond, break this one, break this one. So can you guys see it's a difference in docking between it being perfectly overlapped versus being kind of on one side exclusively. So the cyclopentadiene is hovering directly over the dienophile. And when we draw our final product, we now have this. Let me draw this a little bit better. These hydrogens sticking out and the ring kind of sticking underneath. The question is, which one's the right product?
Both are right. That's the reason why you show us.
There's actually something in organic chemistry called the endo rule, and it says that most of the time the endo product is preferred. Is more common.
What do you mean more common?
Meaning, most of the Diels Alder reactions you see will observe this stereochemical pathway. There are always exceptions in organic chemistry, and there are different methods you can do to favor the exo product. However, the endo product is more common. And the reason it's more common is that you end up with this whole stabilization of this very electron-rich system interacting with the other electron-rich system from our dyene. So it actually prefers to dock perfectly overlaid rather than offset, and that leads to our endo product. Clear as mud?
Yeah.
So can you represent that again back in 3D structure?
Using the top structure?
Yeah.
Wait.
How about this? We're running out of time. Tomorrow what we'll do is we'll come back to our endo versus exo rule, and we'll learn to draw it in a few different ways. But I just wanted to at least get it presented today.